Here we're going to solve a linear programming problem. For this problem, we want to maximize our objective function, z equals 5x plus 8y, subject to these constraints. We need x greater than or equal to 0, 2x plus y less than or equal to 8, and x minus 3y to be less than or equal to negative 3. We work with each one of these inequalities and graph the system of inequalities. The solution set makes up our feasible region. So we're going to go ahead and sketch a graph. We're going to draw a grid over here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We're going to use a scale of 2. So we're going to go up to 12, 6, and 12 there. And we're going to look at each of these inequalities and then sketch the system of inequalities. So here we have x greater than or equal to 0. If we consider the equation x equal to 0, x equal to 0 is the y-axis. We want x to be greater than or equal to 0, so that puts us over here to the right. Look at our next inequality, 2x plus y is less than or equal to 8. If we set that up as an equation and solve for y, we get that y is equal to negative 2x plus 8. We want to go ahead and graph the line y equals negative 2x plus 8. Our inequality is non-strict, so we're going to use a solid line. Pick a couple of points. If we let x equal 0, we'll get y is equal to 8. If we let x equal to 4, y will equal 0. Connect those 2 points. And we're going to need to shade the half plane that satisfies this inequality. If we pick a test point, say the origin 0, 0, and put that into our inequality, we'll get 0 plus 0, that equals 0. 0 is less than or equal to 8. That's a true statement. So we're going to shade the half plane that is below our line. So we're going to shade this region right there. Next, we're going to look at our last inequality constraint. We have x minus 3y is less than or equal to negative 3. If we consider that as an equation, x minus 3y equals negative 3. Again, we're going to solve for y. Negative 3y equals negative x minus 3. Y is equal to 1/3 x plus 1. The inequality is non-strict, so we're going to graph this line with a solid line. We need a couple of points again. If we let x equal 0, y is equal to 1. That'll put us right there. And if we let x equal 3, then y will equal 2. Go 3, 2. I'm going to go ahead and graph that. So here we have y is equal to 1/3 x plus 1. And this line is y equals negative 2x plus 8. We want to again shade the half plane that satisfies this inequality. So we're going to pick a test point. We'll use 0, 0 since it's not on the graph of our line. 0 minus 3 times 0, that's still 0. 0 less than or equal to negative 3, that's a false statement. So we want to shade the half plane that does not contain 0, 0, which means we're going to shade above that line. So we're going to shade this region here. Now our feasible region for this problem is going to be where the overlap lies. We need to be to the right of the y-axis. We need to be above the line y equals 1/3 x plus 1. And we need to be below the line y equals negative 2x plus 8. That puts us in this region right here, this triangular region. We need to find the corner points for this region. Let's see, these are going to be y-intercepts for our two lines. And we'll need to find the intersection point for that line. So our corner points, so far we have this point right here. This is going to be 0, 1. That's the y-intercept for this line. This point is 0, 8. That's the y-intercept for that line. We need to find out where those two lines cross. So we're going to set the two y's equal to each other. So we'll have negative 2x plus 8 equals 1/3 x plus 1. We need to solve this for x. We'll go ahead and subtract 1/3 x from both sides. So this will be negative 7/3 x plus 8 equals 1. Negative 7/3 x. We subtract 8 will be negative 7. We're going to multiply both sides by negative 3/7. We'll get that x is equal to 3. We know the x value is 3. If we plug that into our equation here, we'll see that y is equal to 2. And so this is our point of intersection, 3, 2. So we have 3 corner points, 0, 8, 0, 1, and 3, 2. Since we know that the maximum value of our objective function must occur at one of the corner points, we simply evaluate the objective function at each of our 3 corner points. So we're going to list our corner points, and we're going to use those to evaluate the objective function. So we have 3 corner points, 0, 8, 0, 1, and 3, 2. Put in 0, 8 into our objective function, we'll have 5 times 0 plus 8 times 8. That gives us a value of 64. Put in 0, 1, 5 times 0 plus 8 times 1 gives us a value of 8. 3 times 2, 3, 2. We get 5 times 3 is 15 plus 8 times 2. So we get 15 plus 16, which is 31. So we can see that the maximum value for our objective function is 64, and it occurs at the point 0, 8.